Basic automatic controls. Unit 13, Introduction to Automatic Controls. Objective. After studying this unit, you should be able to define bimetals, make general comparisons between different bimetals applications, describe the rod and tube, describe fluid field controls. Adjective continue. Describe particular liquid particles, partial vapor field controls. Distinguish between the below's diagram and Bourdonnaire. 2. Discuss the thermocouple. Explain the thermostat. Thermistor.
Types of automatic controls. Electrical, control electrical devices. Mechanical, used to control fluid flow. Electromechanical, provide electrical functions or control fluid flow. Electronic, use electronic circuitry.
Devices that respond to thermal change. Thermostats, intended to maintain the desired temperature in an occupied space or refrigeration system. Safety devices, protect equipment and people from damage and injury by disabling a system if unsafe temperature conditions exist. The bimetal device consists of two dissimilar metal strips, brass, steel. Strips have different rates of expansion and contraction. When heated, the device warps to start, stop, or modulate electric or fluid flow. Rod and tube, type of bimetal control. Snap disc, quick open, quick close device.
Okay, here's a cartoon, your first cartoon of the day. This is a bimetal. It consists of two different metals. What kind of metals are they?
Brass and steel.
Brass and steel. Okay, these are bimetals here. I'll pass these around so you guys have a chance to have hands on. These bimetals are wrapped in a coil, which gives it more movement. This one here is a fan switch. So the deal sticks in the heat exchanger, it heats up and it moves that little dial. See that? Isn't that amazing?
Fantastic.
Fantastic. That's the type, those are just types of bimetals. A bimetal device, if we were to make a crude switch out of it, that's how we would do it. See that? See how it makes sense? That makes sense, huh? You have there, you have a set of contacts, and it warps, and it opens a set of contacts. Wow. That's bimetal. There's a lot of our controls are bimetal. Especially in safeties and thermostats, etc. Everybody has one of these. You recognize it? I know it's a cartoon.
Yeah, it's cartoon.
It goes in a
Thermostat.
water tank. A water tank. So it actually moves this way, pivots. As the water gets colder, it opens the burner to start the burner on the what?
The burner. A water heater.
The water heater. Okay, so we have what we call a water heater. It's not a hot water heater. Because if you had hot water, why would you need to heat it?
Make it hotter.
When the water in there is hot.
Yeah, it's gonna be hot, you know?
Then it would be called a hotter water heater.
Sounds like a plan.
It's a water heater,
That sounds like a little.
a hot water tank or a water heater, okay? Okay, here's another cartoon of a snap disc, and what they call is the same thing, it's a bimetal, it's a snap disc. So as you can see that as it heats up, this shown as it heats up, this is in the cold position most of the time. As it heats up, it warps and it snaps open, or it warps. So it disconnects a circuit, let's say. Okay? You good with that so far? That's exciting. I don't have one of those, so you can play around with touch. But you get the idea.
Controlled by fluid expansion. Fluid inside a closed container expands and contracts as temperature changes. Expansion, contraction converted to motion. A thin, flexible diaphragm facilitates motion. Bolt filled with violate fluid connects to the diaphragm by means of a transmission tube. Partially filled bulbs provide accurate control. Bellows are used when more movement is needed.
Okay, so we have here a diaphragm and a bulb filled with volatile fluid. Okay, so you can see the diaphragm underneath there. As this heats up, it expands and puts pressure on the diaphragm, and it moves the diaphragm. Well, hands on.
Manometer.
Okay.
So it's totally enclosed, it will move the diaphragm. Now, they're talking about bellows. Now, bellows are a little different. They work on the same principle, except bellows actually give you more movement. So bellows is like an accordion thing, accordion looking thing. Right? You got that? Accordion thing. Squeeze box thing.
Is that gonna be on the test?
Good, thank you. Yeah, might as well be.
For sure.
Wow, you had to talk.
What else are you gonna put on the tester?
Yes, it's on a test. And here is a cartoon of the thing in action. As pressure increases with the volatile fluid, it moves that bellows up and gives it some kind of movement. So as this bulb cools down, that bellows moves down. As the pressure decreases by temperature. So what is a volatile fluid? Anybody know? Anybody know what volatile means? Anybody here? No? What they're talking about, a volatile fluid is basically it's refrigerant
Wow.
that expands and contracts according to
Heat.
heat. Yeah, so it'll increase its pressure with heat, decrease its pressure with cold. Oh, look, another cartoon. This is a bunch of cartoons on this, huh? So here you have, this is an example, another crude example of a bellows controlling a refrigerator. So you have 30 degrees inside the refrigerator. The contacts are open. The bulb is on the inside of the refrigerator. Check it out, right here. Right? As the refrigerator warms up, as you can see, the bulb warms up. It puts pressure on the tube and it moves that diaphragm and it pivots and closes a set of contacts. That's how it can be, that's how a refrigerator can be controlled. The contacts, electrically start condensing in it to start the refrigeration cycle to cool down the box. Isn't that exciting? I think that's exciting, even though it's a pretty crude demonstration. But it's how it used, basically. It's how the diaphragm control is used. Here's a cartoon of a bellows. These are bellows. It says, acts like an accordion. I said that already. Yeah. Accordion, to reverse when the pressure is under the diaphragm is increased, the diaphragm expands. Again, it's controlled by that volatile fluid. Okay? And we also have the bourdon tube. This bourdon tube is hooked to a volatile fluid, as you can see, and it looks like it's temperature. It's reading temperature, so as the pressure increases, this tube starts to straighten out. So as it starts to straighten out, it pivots and moves a little needle indicating what temperature it is according to that pressure.
So it's kind of like a gauge.
It is. This is what's in our gauges. The bourdon tube. Whoa.
The thermocouple consists of two dissimilar metals joined to end and has a hot and cold junction. Heat to the hot junction causes current flow, generates about 20 millivolts when heated. Used in gas appliances to detect pilot light, the signal permits main gas valve to open. Thermopiles equal multiple thermocouples. Thermopiles generate 500 to 800 millivolts.
Okay, it says two dissimilar metals. What kind of metals are they?
Brass.
What?
Would it be like brass and steel like the other device, or
Huh?
would it be like brass and steel, or would it be something else?
No. That's a bimetal. This is different than a bimetal. I guess I could look it up in the book. Yeah. Since nobody has been prepared.
Yeah.
Yeah. Knows all about it. Right?
Well, Steve, getting us in trouble.
Usually light, unlike metals such as iron and tin.
Okay. Where is it? Where is it?
Page 333.
333, see? Can't find it, okay.
13.5.
Constantan, and iron and Constantan, okay. You got that?
Yeah.
Okay, so this is a thermocouple. This is in a pilot assembly. With an electronic igniter. Seeing that? You seeing that? Are you seeing that?
I have eyes, yes.
Okay. Now, we also talked about thermal piles, which are multiple thermocouples. This is a thermal pile. So the thermal pile is what? What is a thermal pile?
Multiple thermal
Multiple
couples,
thermocouples generate about what?
500 to
800 milliamps?
Yeah.
Okay. This one is broken at the end, but you can see these are used, they were used years ago in floor furnaces. If you have a wall furnace, anybody have a wall furnace? You have a wall furnace? You have one of those. You have one of those in there controlling the gas valve and it's actually controlling the heat. So if you ever notice that your power goes out in your house, you still have heat. Because that generates enough power to open and close the gas valve. Oh, wow. So how many is 500 to 800 millivolts? How many volts is that?
It's like 8 volts.
No, it's like a 0.8, 0.5.
Yeah. It's like branches up there.
So what is 0.8, 0.5?
Yeah.
What is that?
5 volts.
How many?
Volt or 0.5.
What's 0.5? How many 0.5?
Half a volt.
Half a volt. So it generates around a half a volt, right? Almost a volt. 800 millivolts would be almost a volt, right?
Yeah.
Okay. So it's got some voltage there, huh?
Yep.
For just from the flame, from the generation of the heat from the flame.
You forget how to do this. You forgot how to do it.
Stop.
First thing you think, you don't have to.
Okay, so here is the action photo. This is what the thermocouple does. As the pilot heats it up, like in the cartoon, it sends a little signal, about 20, 30 millivolts, and it holds open this little coil. And this little coil has a little latch on it, and it allows the main gas to open and close. Now, if it was cold, this latch would hold that valve so it couldn't open. Okay? Anybody ever light their water heater?
Wait, what?
You have. One person has lit a water heater.
I did it too.
Water heater.
Huh?
I did it alone.
Okay. You notice the little knob that you have to push down and hold down? You know what that is?
I'll say this. Yeah,
That's
it's
that.
Oh, okay.
So you're holding it down until this generates enough voltage to hold it on its own. Okay? Oh, boy.
Electronic temperature sensing devices. Thermistors are electronic solid-state devices where resistance changes in response to temperature, used in electronic circuits to modulate responses, and can be used to provide temperature readings. Electronic temperature sensing devices continue the positive temperatures coefficient, TTC, increases the resistance as the temperature increases. The negative temperature coefficient, NTC, decreases resistance as the temperature increases.
So in thermistors, here is a thermistor. This is an example of a thermistor. Is that what?
Tell you about coffee.
Oh. So you can touch that. Here's another example of a thermistor. It's one of these. This is called what we call Surak.
Whoa.
As it says Surak on it. That's Spock's father. Surak. This is used for starting compressors. As the current goes through it, it heats it up, and it opens, it makes so much resistance in that control that no current can go through it.
Summary. Automatic controls can be electric, mechanical, electromechanical, or electronics. Thermostats, safety devices respond to temperature changes. Bimetal strips warp with changes in temperature. Fluid expansion controls convert increases or decreases in pressure to usable motion. Heating a thermocouple generates millivolt signals. The PTC and NTC change resistance with temperature changes.
I'll just show you.